In this lesson, we are going to consider the physics of what's going on at the top of the vertical circle. So, we have gravity that's always acting. Gravity at the top is pointed which way? That's right, it's pointed down, but really you should be saying toward the center. It's inward, considering the circle up at the top, right? Since it's pointing toward the center, that's centripetal. It is a real force providing some or all of the centripetal force needed for the particular situation. Then there's a support force, and a support force is passive. It adjusts itself so that it equals the value needed to accomplish the job at hand. And when you add it as a vector with gravity, you get the centripetal force. There, are you ready for a test now? Okay, let's look at this a little more carefully first. So, vertical circular motion, up at the top, we can divide it into three categories. We have the condition of too slow. I'm not defining what that means yet. You might figure it out before I tell you. That'd be good. Too slow is like a Ferris wheel, a too slow situation. What's a too fast situation? That'd be a roller coaster loop where you're going upside down. And then there's the just right, like a roller coaster hump or bump at Great America, if you've ever been there. That would be like the Viper. It has roller coaster. It has humps and bumps where you feel like you're just floating over those particular structures, the humps and bumps. Let's start with the too slow scenario, like a Ferris wheel. Okay. Here is a person up at the top of the Ferris wheel. Hopefully you're not too bored. It's actually kind of a nice sight usually. It's very peaceful being on a Ferris wheel. You're not getting the amusement park ride jitters from this so much. All right, so we have gravity. Gravity is always there. And what other force acts on you? You could close your eyes and visualize. It's something you feel. You actually feel a force, and it's pretty sizable. And it's called the support force. In this case, a seat force. Pushing up on you. I hope you feel that. If you're on a Ferris wheel and don't feel that, something's drastically wrong. Like maybe the seat became disconnected from the structure and you're free falling. It's not going to be a happy day for you if that's the case. This, in fact, is the path you would take if suddenly the support force was gone. You'd go bonk and you'd land on the ground. Not a pleasant experience, typically. I think that's it. There's no other real forces acting, so let's add the forces. Here's gravity, and then tail to tip is the support force. Now, my claim is that the vector addition gives you centripetal force. So there it is, centripetal force. Notice centripetal force is small, but you would expect it to be small because on a roller coaster, you're moving slowly. You don't need a lot of centripetal acceleration. You don't have a lot, so therefore you don't need very much centripetal force. So really, in reality, these two forces almost cancel. Just a little bit of inward force is needed to execute the circle. Commenting on the directions, support force is up, gravity is down, Fc is down. And now we're going to write the magnitude equation. So we start by saying Fc. All right, Fc, the net force. It's the result of the forces in the same direction and in the opposite direction. And we start with the forces in the same direction. So it's mg minus fs. And since we have an equation for Fc, we will go ahead and write it. I typically start with mv squared over r, but you might want to write m 4 pi squared r over t squared, depending on what you're trying to find. So this idea just comes from that the sum of the forces equals the centripetal force. Well, now it's time to consider the too fast scenario. You're on the inside loop of a roller coaster, and you may recognize from experience, if you've had this experience, that you better be going pretty fast to execute that loop. Well, there's a reason for that. So we have mg acting down. And now the question is there a support force? Is a support force acting on you? And there's really only two possibilities. Either you're feeling a seat force or you're feeling a shoulder strap force. Now, which of these are you feeling, if any? Okay? Well, if you close your eyes and think about it, you might be hearing an alarm going off in the distance. What is that? That stupid thing. Ah. Okay. All right. Shut that alarm off. Sorry about that. So, the shoulder strap holding you in, if that's pushing on you, well, that means it would be pushing up on you. That's not going to happen unless this thing gets hung up at the top and stops and you try and come out, then the shoulder strap pushes up on you. If you're thinking about it correctly, the seat is shoving on your bottom. Yes, it is. And so there it is in the same direction as gravity. That's a little mysterious. Those are the two real forces acting on you right there. Now, if there was no support force, that's right, you would go sailing off like this. And that's not a very pleasant scenario. Okay, let's add the vectors. So here we have mg, and there we have Fs, seat force or support force, giving you the centripetal force. Support force is down, gravity is down, Fc is down. Notice that Fc is just a combined of both of these because they're both inward forces. So Fc is large, consistent with a large centripetal acceleration, consistent with a very fast motion, mv squared over r, or for acceleration, v squared over r. V is large, a sub c, and thus F sub c is large. So the magnitude equation, Fc is mg plus Fs, which is mv squared over r. And there you have it. One more is the just right. What is just right? It's the experience of floating or feeling weightless. So if you have a hump or bump, such as on the Viper at Six Flags, you kind of feel like you're floating over those bumps. Now, that's the sensation associated with, feeling like your innards are coming up into your throat. You ever wonder why that is? Well, it's because it actually is. Well, to a certain extent, because the support forces, namely the tissues holding your kidneys and intestines and stomach and heart all in place, relax. And so they rise up a little bit. Those organs actually rise up inside you. Are you enjoying this conversation? I'll stop. We have mg acting down and support force. Well, again, there is none. Nothing is pushing on you. You don't feel any contact forces. The seat isn't shoving on you, and the shoulder straps, likewise, are probably not pushing on you. So when we add the vectors, it's really complex. There it is. So the sum of those vectors, which is just mg, gives us Fc. There it is. The centripetal force is just the weight. Support force is 0, gravity's down, Fc is down. The magnitude equation, Fc equals mg. So since that's mv squared over r, you can just, cancel out the m's and you have a real nice little relationship there for the just right scenario. If all the centripetal force is provided by gravity, then no support force is needed. It turns out that it is the support force which gives you the sensation of weight. Doesn't mean your weight is gone because you still have mg, but you don't feel anything pushing or pressing on you. Your body is not subjected to compressional or elongation forces of any sort. So you feel weightless, even though you're not weightless. A huge distinction. Now, have you figured out what too slow, too fast, just right, what the common element is? Well, let me say it really is the role of gravity. In the too slow scenario, gravity was too much. Gravity pulling down, with this up on top, gravity pulling down, that was too much because centripetal force is so small you needed just a little bit. So support force was the opposite way. So gravity was too much there. With it too fast, gravity is not enough. It needs a support force to help it to execute the circle at such a high speed. In the just right, gravity is just right. Gravity uniquely provides the centripetal force required to execute the bump. And so these are designed in such a way so that the speed you're going over the bump or hump is such that the centripetal force required equals your weight. And if it's designed that way, then you get that wonderful weightless sensation. And that is a summary of the physics of the top of a vertical circle.